Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 6, Lesson 6, Translations of Exponential Functions. After this lesson, you'll be able to perform, analyze, and use transformations of exponential functions. Think back to Topic 3 again. When we did transformations of linear functions, the same rules are going to apply. In the model and discuss, we have this graph representing a radio station, and they have this function to represent the growth of band A's fan base. So if I remember my exponential functions, I know the 100 represents the initial value, so they started out with 100 fans, and the growth rate is 3, so they're tripling. They're multiplying by 3 over and over again, looks like every month. Part A, what would the graph of the function look like for band B with the fan base growing twice as fast? So if it's growing twice as fast, that means instead of multiplying by 3, what are we multiplying by? We are multiplying by 6 every time, so that would be B. B would be 6. So our equation would be, I can write the equation really quick, 100 times 6 to the x. And so if we're starting at the same value, it's going to be going from 100, then it's going to be at 200, then it's going, 100, then it's going to be at 600, and then tripling, it's going to be way up here, okay, like 1800. So it's going to be growing a lot faster. You can see it should be steeper. So band B, they'll start at the same initial value, but band B's graph is steeper. It's more narrow. It's like a vertical stretch, right? Because we've changed our multiplying factor. Suppose band C, so now we have a new band. Band C starts with a fan base of 200. So now A equals 200. Our initial value is 200, and it's growing twice as fast as band A. So if it's growing twice as fast, its growth factor is also 6. So we could write the equation really quick. 200 times 6 to the x. So how would we graph that? Well, the initial value would be at 200, and then we multiply by 6. So 200 times 6 is 1200. Okay, it's going to be looking like that. So it's similar to band B, except we've shifted it up, right? We've shifted it vertically. So C is going to be a vertical translation of B, because the growth rate is the same, but we started at a higher, so our initial value changed. How do changes in an exponential function relate to translations of its graph? So again, just like we did with linear functions, just like we did with absolute value functions, the transformation rules are going to be the same, whether we're changing the input or whether we're changing the output. So, vertical translations, if it's vertical, I know I'm changing the output because I'm changing along the y-axis. If we remember initially, with linear functions, we're changing outside the parentheses. Okay, so we can think of there being invisible parentheses. I'm going to zoom in. There's going to be little parentheses around our input. Okay, so if we're changing around our input or outside of our input, outside of those parentheses, like we are here, we're just adding k. This is going to be a vertical shift. We're shifting the whole output because we're still going to double, but then we're going to add a number. So our parent function is just 2 to the x, right? Our parent function is just 2 to the x. If we have a plus 3, now let's figure out what that is in a table. So 2 to the s. Here is our input values. Again, just choosing a little bit to the left and a little bit to the right for our inputs. If I plug in -2 into my function rule, I would get 1/4. 2 to the -1/4, 2 to the -2 is 1 over 2 squared. Okay, that's just a quick review. If we add it and then add 3, well, 1/4 plus 3 is going to be 3 1/4. And then we could do the same for the other inputs. Okay, 2 to the 0 is 1, and then I add 3, I get 4. So all we're doing is we're taking f of x, our parent function here, and all we're doing then is adding 3 to get to g of x. That's all we're doing there. Okay, and we could graph those points. We could graph x comma g of x, and then we would be graphing j of x by subtracting 3. So then we're going to take f of x, and then we're going to subtract. So we're going to take 2 to the x and then subtract 3. So we would take 1/4 and subtract 3 to get j of x. That's what we're doing. So we have these values in our table, and we graph them. F of x is the black function, that's our parent function. G of x is the blue one. What happened? We shifted all of the values up 3 because we added 3 to all the values. And j of x is down 3 from the parent function because we subtracted 3 from the parent function. So these are vertical translations. Again, the rule is just whatever that value is. If it's positive, we go up. If it's negative, we're shifting down. Try it number 1. How does the graph of g of x compare to the graph of f of x? So again, we're comparing to the parent function. So this is my parent function. How does g of x compare? Okay, well, what's the change? I have a change outside my parentheses. I have a plus k, so that means I'm shifting up 1. That's it. I just shift the whole graph up 1. For j of x, what are we doing? Well, same thing. We have a change outside the parentheses, but now we have a negative 1. K is negative 1, so we are shifting down 1 from the parent function. Hopefully this lesson goes pretty quickly because we've done these transformation rules 2 other times before. Example 2, horizontal translations. So if we're talking about horizontal translations, we're moving along the x-axis. That means we are going to be changing our input. We're changing inside the parentheses. So you can see here, that's modeled with this x minus h. Now there's a change inside those inputs, inside the little invisible parentheses that we would have. Okay, so inside those parentheses, we have a change. And we have to think it's also opposite. So if we were to graph something, in order to get back to the parent function, we have to add h. Okay, so it's shifting in the opposite direction. So let's say h equals 5, and let's compare parent function. So here's our graph of our parent function. Okay, it goes through 1, and graphing g of x, where we do x minus 5, if we plug that into our graphing calculator, we can see that it shifts to the right, even though we have x minus 5. That means in order to get it back to the parent function, I have to subtract 5. Okay, because my output, to get to the same output, I have to move the graph to the left 5. I have to subtract 5. Okay, so that means I went from my parent function, shifted right. In order to get back to the parent function, I'd have to subtract h, or 5, to get back. So again, this is the same rule as before. Just remember, if the change is in the parentheses, we're changing horizontally, and you have to watch the sign because it's the opposite direction. Minus h does not mean to the left. It means actually moving to the right. Compare the graph of j of x to the graph of f of x, again, the parent function. So now we still have that change inside the parentheses. Okay, but now our value is going to be negative. We're going to say x is negative 3. So what would that look like? 2 to the x minus negative 3, right? So that becomes 2 to the x plus 3. So our input has shifted, and that means our whole graph is going to move to the left, because to get the same output, so to get my same output, I have to add 3 to my input. Do you see? So to get this output right here, to get it back to the parent function, I have to add 3. There's 3 hops from here to here. My input has to increase by 3 in order to match up with the parent function. Try it number 2. Compare the graph of each function with the graph of the parent function. Okay, so that's our parent function. We're just looking for the changes. For part A, we have a change in the input. We're changing inside the parentheses, and I have to remember I'm going to move in the opposite direction, so I'm moving to the left too. For part B, we again have a change inside the parentheses. So we're changing horizontally, and we have to remember, in order to get back to the parent function, we're actually moving to the right. Okay, so this is a shift horizontally to the right 2 units. Example 3, how can we compare the properties of G given this table to the properties J given in the graph? Okay, so we're comparing G of x and J of x to the parent function, but we have a table for G of x and we have a graph of J of x. So we need to compare those, what's happening between them, between G and J. So the y-intercept, we can tell just from the table, we can tell the y-intercept for G is 3. Compared to the parent function, that seems like I've shifted up 2, right? So G of x has shifted up 2. How about J of x? What's happened? Going from here to here, where's my y-intercept? It's down 1. So J of x has shifted down 1. Okay, but if it's an exponential function, then that means the asymptote is also going to shift. Okay, so instead of being at 0, where the parent function is, we have to shift the asymptote down 1 as well. So now the asymptote is going to be at -1. The asymptote also shifts down. The line that it approaches but never gets to also shifts down 1. Okay? And for G of x, the asymptote then would shift up 2. So the asymptote of G, instead of being at 0, it's going to be shifted up 2. So it's going to be at 2, y equals 2. So since the asymptote is up at y equals 2, then the range is going to be everything greater than 2, right? Because it's now approaching this. That didn't match very well. So now it's just approaching +2. So the range is everything greater than 2. It never gets to 2. The domain is still going to be all real numbers. So what about for J of x? Well, now the range would be everything greater than -1. So since we know that the range for J of x is greater than -1, because again, we moved the asymptote down 1 unit, and the domain is still all real numbers, if we're comparing G to J, so remember G was up here at 2, what's the difference between G and J? There's a difference of 3, right? There's a difference of 3, so J is 3 units down from G, or G is 3 units up from J. So it depends on which one you start with. I think we would start with G, because that's first alphabetically. So G is our new parent function. That's where we start. To get to J, we shift down 3 units. Try it 3. The graph of the function B is a vertical translation of the graph of A, which looks similar to a parent function. So here's A, and it has a y-intercept of 0. So what does that mean? Okay, so for B, we know, if I'm going to write an equation for B of x, it's going to only have a change to the outside. So it'll have a plus k or a minus k, we don't know. But it has a y-intercept of 0. So normally, this parent function, it would have a y-intercept of 1. So then if the y-intercept is 0, that means we must have shifted down 1, correct? So B of x would be a -1 because we've shifted our y-intercept down. C of x, they've already given to us, looks like we've shifted up 1. So what's the difference between B and C? If I've gone down 1 and then I went up 1, well, if I just look at a number line, and here's 0, we're going to call A 0. And for B, I went down 1 to -1. For C, I went up 1. What's the difference between B and C? Well, the difference is 2. They're 2 units apart. Or there's a vertical translation of 2 units from B and C. Part B, how does the graph for M compared to P? So what's the difference? I've gone down 3 from a parent function, and then I went up 4. So let's look again at our vertical number line. If we're going to call 0 our parent function, there's no vertical translations. So here's our parent function. M is 3 units down, and P is 4 units up. What's the difference between M and P? The difference is going to be 7, or -7. We made it to the concept summary for translations of exponential functions. Just remember the rules. If it's outside the parentheses, we're changing vertically. If it's inside the parentheses, we're changing horizontally. and make sure you keep track of the directions. If you have any questions, put them in the comments. Make sure to like and subscribe, and come back for topic 7.